22 attendees, so the previous class is going on. So are you able to see the screen?
Yes, sir.
Yes, sir.
Great, great.
Sir, yesterday you were talking about uncountably infinite.
Yes, that question. So, I mean, yeah, let me just do the recap so that, I mean, that in the meantime, people will join. So we have done linear vector spaces, examples, properties, subspaces, and then we come to very important concept. That is that few vectors in certain cases can be used to span or generate the whole of the linear vector space. So those few vectors must be linearly independent and must be able to span the space in order to be basis. And this basis can be finite dimensional and infinite dimensional. In the infinite dimensional, it can itself be a discrete one, so vector space of polynomials, but it can also be continuous one, and that's the question. Yes, I did ask. So somebody.
Sir, we cannot find the exact answer, but sir, I guess for we need to calculate. If we need to calculate uncountably finite, then it must be with some with respect to something else.
With
Means
respect to something else means what? I mean, in principle, when we are talking about the basis, we are saying that there exists a vector space, and for that particular vector space, we are talking about the basis vectors. So, in respect to that, of course, we are talking about vector space. Surely, it has to be a vector space, right?
yes, sir.
And it can be vector space of
Yes, sir.
anything which looks continuous to you. Yeah.
So,
Okay. We have equal time. Yeah. Please
on
go ahead.
searching a bit about this,
Right.
I
Yeah, just
came
do
to
the
know
Google
that
search.
Dirac delta function,
Yeah. Right. Okay.
yes, sir,
Good
so
point.
Dirac delta function kind of consists something like uncountable infinite
So,
basis, at
right.
least
That is
uncountable basis.
nice. Except that I would just request you to associate it with something. Direct delta function is something which we define as a function, of course, in a continuous space, so that things are there non-zero at a particular point and zero everywhere else. Right. So when we are defining it, so if there is a continuous function and we have some multiplication with the direct delta function, then what we say that that function is existing only at that particular point. Right. I mean, this is what we try to say. It is true. I mean, you are in the right direction, except that you have to correlate with your quantum mechanics. I mean, basically, we are going to use continuous infinite dimensional space to even speak about the simplest of the wave function. What wave function do you start with? When you started with the concept of wave function, which wave function did you actually try to solve? Xi as the argument of which argument? So
X
short
and
engineering
t,
question.
position and
Yeah.
time.
Position, time, right. So position itself, for example, think about it. If somehow you think about position, then that position itself is a real number. But then you have to correlate with the vector space, that what kind of vector space will have position in it.
So, sir, is the answer Hilbert space here?
No, I'm not going to answer now, but I will continue to give you certain points, and we will reach to the point where we will discuss this concept continuous infinite dimensional basis a little bit in detail. So we will reach there. In the meantime, yeah, please continue to read any quantum mechanics book, all the quantum mechanics book. Whenever they talk about the continuous basis, which means whenever they are talking about the direct delta function, they should be talking about this.
Sir, are you talking about plane waves?
I mean, you can say in some sense, yes, plane waves, sure. And but how are you going to relate it with the vector space? That's the question. How are you relating the plane wave with the vector space? That's it. Nothing beyond that. Yeah. So answer is not that tricky, but okay, we will discuss it later on. Today, what I want to show. I mean, are the students there now? 10:07, 127. Okay, we have. So let's start today's concept. And please don't worry, we are going to take this concept surely in our subsequent classes. So the concept which we are going to deal with today is what we call as the inner product space. So you have already now understood what a linear vector space is. What we are going to do actually is to go to next space, which is part of the linear vector space. What we are going to say that the vectors of the linear vector space, if they follow a certain properties, then they qualify to be called the inner product space. And what we are going to do, basically, I am going to use the complex linear vector space, but this can be easily extended to real linear vector space. The reason why I am taking the complex linear vector spaces, because our quantum mechanics will utilize it. So I will give you an idea, I will give you the introduction, and then I will come with the physical significance of why do we want to have that. So let's just go ahead with it. Now, in the case of 3D vector, so let me just take some cues from there. In the case of three-dimensional vector, if I say A dot B, what does it mean? So a dot product.
Multiplying
Yeah.
the corresponding components and
Function
add
of A vector on B vector.
So what will be the result? Will it be a vector or will it be
a
something
scalar.
like?
Scalar.
Scalar. This is what you are saying, that we can write it something like ax bx plus ay by in case if these are the components, right?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Is it always I can write this ax bx ay by az bz, or you are talking about some basis here?
So it has to be an orthogonal basis.
It has to be on the in the orthogonal basis. We can write down components in this form. Okay, absolutely fine. But the important point is this dot signifies to you that either we are talking about a scalar product or a dot product, so that if the two vectors are considered in this space. So let me just take the liberty that if there are two vectors in this space, then that takes me to a real space. Not only that, this guy also obeys certain properties. I mean, look into this. Is this true or not?
Yes.
Yes,
Yes.
sir.
sir.
Yes, sir.
Okay, good. What about A dot A?
Yes.
Can you say something about A dot A?
Magnitude.
It's the magnitude of A.
So I can write down this as, let's say, norm square or magnitude square, and this is going to be always a negative number, positive number, or what?
Always a
Positive.
positive.
Always a
Always
positive number.
Positive.
Positive.
Okay, so let me write down that positive or equal to 0. When will it be equal to 0? A dot A?
Zero vector.
When
Null
A is zero.
vector. In case
Null
of
vector.
null
Only
vector.
for a null vector.
In
Null
case,
vector.
In
so
case of null
equal to
vector.
0 if A vector is a null vector. Or what about, okay, let me ask you this. So A vector, so A, B plus, okay, notations are such that small a and small b are real numbers. So what will be the dot product of vector A with this?
We follow
A
simple
dot B
distributive
plus
property.
Small
Scalar
a dot
scalar
b
Plus
A
Distributive
dot
property.
A dot
Plus
C.
plus small b
A dot C.
Small b
a
A
dot
vector
c.
dot C vector.
So you see that it's not only that the dot product is giving you a scalar, but that dot product is also fulfilling certain properties. This allows us, of course, one, to give us an idea of length, because the way you said that it is a magnitude of the vector. So several times we only write it this. It's absolutely fine here. But it also gives us direction. So if I want to find out direction between two vectors, so cos theta. How do I define that?
Sir,
Dot product.
A dot B
A dot b
A dot
divided by magnitude of a.
magnitude of A.
Magnitude of A.
Magnitude
B.
Magnitude of B.
So we have direction coming in, length coming in. We are just going to generalize this three-dimensional dot product to what we will call as the inner product. So we are still talking about the vectors, but now we are going to talk about a space in which the vectors satisfy a certain properties, just like this scalar product is there. So let me just first write down and then we will discuss it. So inner product, how am I defining it? It's a function or a map that associates a complex number instead of a real number, a complex number with a pair of vectors. So now we are talking about the generalized vector space. And since I'm talking about the complex, so I'm writing complex. Doesn't matter. I mean, I can even write VF, and that is fine. In such a way that following properties hold true. Okay. So first, I have to define. I mean, something like dot. I could have defined dot, but that's not a common way of defining it. So let me just define it. So I am defining one side of a bracket, another side of a bracket, and this. This I will define as the scalar product, dot product, or inner product, such that whenever I am writing this triangle bracket and a comma between two vectors, this is always going to give me a complex number. So in some sense, you can say there exists an operation which we call as the dot product in this case, which takes us such that two vectors of the vector spaces into a complex number. So we are associating a complex number with two vectors, just like we were associating a real number with two vectors in the three-dimensional one. What properties? The properties are this: u comma v should be equal to v comma u star. Now what is this star in the case of complex numbers?
Conjugate.
Conjugate.
Conjugate. So we are
Let's
not
conjugate.
taking it right. We are not taking it to be symmetric. We are saying it is a conjugate symmetric. Okay, this is one. Second is exactly what we read: 0 greater than equal to 0, and this will be equal to 0 if and only if my u vector is 0 vector, just like the way we wrote for this. And third, okay, u with v plus w. So if the addition of two vectors, and please see now I am writing just a simple plus, although you can, okay, let me just write it, and then please see that here I am talking about addition of two vectors, whereas here I am talking about addition of two, what are these brackets?
Complex numbers.
Complex numbers. So just remember that. I mean, in the books, it is used like this, but please remember that when we are talking about v plus w, it is the two vectors which are. And final one, u alpha v is equal to alpha u comma v, where alpha is any complex number. So we have written four properties that if somehow we can define a bracket like this, which ultimately gives me a complex number and which ensures that following four properties hold true, then that space is called the inner product space. In some sense, you can tell it that if with my vector space, the vectors also obey certain rules for the scalar product, then I call it a inner product space. First question on the inner product space, and then I will tell you why these properties and what will these properties tell us. I mean, one question, of course, is coming to your mind that why are we even defining this inner product space? Of course, length and direction, we will discuss about it. But why are we even defining? So those things we will try to answer here. I am pretty sure your quantum mechanics teacher will also try to do that. But let's just try to do. Okay. Now, why I have defined first one, u comma v is equal to v comma u star and not v comma u. So let's just think about it. If I have u comma u, what will be the first property? What will first property mean?
Greater than equals to 0.
No, the first one. Conjugate symmetry.
Conjugate.
U comma U star.
Conjugate
is equal to U comma U conjugate.
U comma U conjugate.
Which means what?
Conjugate
This-
symmetry.
Yeah, but this puts some constraint on u comma u.
It
Whenever
will be
you are
purely real number.
very good. So now see one thing, even though the product in itself can be a complex number, but by defining this to be conjugate symmetric, the first property, if you look at my product with itself, the product of the vector with itself is going to be a pure real number. And that, you know, I mean, in case those of you who can try to think about it. So what happens if z is equal to z star, where z is a complex number? Yeah. Now, I want to think about u comma u as some sort of a length or magnitude or norm. So if I want to think of the multiplication of vector with itself as a magnitude or length, it has to be a real number. It cannot be a complex number, right? Otherwise, it would be an abstract quantity, a complex number. So in order for u comma u, the inner product with itself, to be defined as the length or the magnitude or the norm, we define this u comma u to be a real number. But even with real number, it's not fulfilling the purpose of length. Why? Because real number can be negative or real number can be positive. And if real number is negative, then what will negative of the length mean? So the second property comes for the rescue. Second property tells you that this real number has to be always greater than equal to 0 and equal to 0 only if the vector itself is 0. So first and second property together allows me to write something what we know, magnitude, length or norm of an abstract vector as, okay, just like the way you defined, so go back previous, just like the way we defined a to be the length. Now, only reason why I am not using single bars and I am using double bars to show that, because single bar in the case of complex number is generally reserved for what? So if I write mod z, what does it mean? Mod z.
Under root x square plus y square.
But
Under root x square plus.
so this is very simple, right? Since our mod z's are generally defined in this manner, or of course you can write it in terms of the real and the imaginary components. So we are using this double symbols for defining the magnitude or length or the norm. So okay, now third property and the fourth property I can actually even combine. Look into this the way I write alpha v plus beta w. So v, u, v, w are all vectors. So u, v, w are all vectors of the vector space, and alpha and beta, they belong to field, which in our case is a complex number. So this just tells us the linearity of the inner product with respect to scalar multiplication and vector addition. So I can write it equal to alpha u comma v plus beta u comma w. So those two we have defined earlier also. So if you just go back, u comma v plus w and u comma alpha v. Remember, we defined vector addition and we defined scalar multiplication with the vector. So we have to have some rule what will happen if this inner product is taken with respect to vector addition or with respect to scalar multiplication. And we say that we are going to use the linearity. So these three properties, if you can see, the conjugate symmetric defining the magnitude or the length and the linearity with respect to both the vector addition and scalar multiplication. These are the three properties that our vector space will have to have in order for that space to be qualified as inner product space. If we do not have this kind of property, then we'll say, okay, it is a vector space, but there is no inner product space which is defined. In the case of three-dimensional vectors, since we define those properties, we will say, yes, three-dimensional vector space is an inner product space. But it's not a complex inner product space, it's a real inner product space. In fact, if you can see that if I associate a real number with the scalar product, then in that case, all the properties which you read about the dot product or the scalar product, that holds true for this space as well. Questions here?
So this
Sir?
property is like
Yes,
commutator
yes, yes.
bracket now.
Yeah, please go ahead.
So I'm saying this property is like commutator bracket now.
Which one is like commutator bracket? I'm sorry.
So can you
No.
please repeat the linearity part again?
Yeah, linearity is that if the inner product is taken with respect to alpha v plus beta w, then this alpha comes out of it. Okay, I mean, let's just look into our previous property. You look at the property of this three-dimensional vector, a vector dot ab plus bc vector, right? This comes naturally to you that you are writing a small a capital A dot b plus small b capital A dot c.
Yes,
Yeah.
sir.
But this is what is called the linearity with respect to vector additions. Remember, this plus is vector addition. The two vectors are added here.
Yes, sir.
Whereas this plus, all are real numbers.
Yes.
So you have to define this property. Yeah, I mean, even though whether you are doing the vector addition plus first and then taking the dot
Then we're
product with
doing
another
the
vector,
okay.
or
Thank you,
you
sir.
are taking the inner product dot product first and then adding this, they are same. That's what we call as the linearity. Yep.
Okay, thank you so much, sir.
Yeah. Oh, this has nothing to do with the commutator bracket. Okay, so about the notation, let me just tell you. In quantum mechanics book, in QM books, you will see a notation like this. This is the famous Dirac bracket. I am not going to say anything about it right now, but I will say something. Let it be there in quantum mechanics class also. Then it is called the ket vector, this V part, and the left hand side is called the bra vector, the U part. So there exist two vectors which comes from what we call as the bracket. This is the famous Dirac notation. I am not taking it because then I will have to define something what we call as the bra vector. And at present, we are just defining the vectors and nothing as the dual of those vectors. So for me, I could have taken a one notation like this. I could have taken a notation like this. This I could have defined, or the way I have defined, which is easier to write, triangle bracket, and it is closest to what it is other than common. And what I am saying that each of this U and each of this V belongs to what? The same vector space. I'm not saying that it is any dual or anything. It is just that there are certain properties that if you change the ordering, then those properties will have to understand. Nothing beyond that. And I will make a correspondence. Just give me some time and I will come up with that once it is done in the quantum mechanics class. So it has nothing to do with your commutator. It is just defining something. So you have a habit of writing a dot b. Every time I write this, you know that it is going to be a real number. But over the period of time, this you understood after doing this vector algebra. I'm just saying that allow me to expand your vector algebra. Instead of writing dot, we are using particular signs because these particular signs become extremely useful in the later part when we will be generalizing this formalism. This particular way of writing helps us. Some of you may think, why don't we just write u dot v? It looks like that we give same importance to first place and the second place. So just to avoid doing that, nothing beyond it. Okay. So this is about the notation which we are using. What else? Some curious questions which immediately come. What will happen to u plus v comma w? So okay, I should just write this, but please understand when I am doing this u. So what will happen to this? What will be the result of this? And how will I get from
U.
it is Yeah, you did say something. Please go ahead. It will be u comma w plus v comma w, something like this, right?
Yes, sir.
Yeah, but you have to derive it from the first properties. So how to do that? We do not know how to take care of this left side, but we know how to take care of the right side. So there are two sides of this comma, right? So let's just use the first property. I can write down this as, this is my first property.
Sir.
Fine.
Yes, sir.
Yes, sir.
Yes, sir.
Right. Now my third property tells me that I can expand this guy, w comma u plus w comma v, right? Now
Yes.
this guy, each of these guys, what? Bracket
These are
w comma
complex
u.
numbers.
They are just complex
a
numbers.
scalar.
So we have the addition of the complex number with this star. So what will be the result?
Complex number.
The
Each
conjugate.
number of the conjugated.
So let me just
Conjugate number.
right. So let me just use it. W comma u star plus w comma v star. Right? Now just use the first property again. What will be the result?
U comma
U comma W.
Sir, u comma w,
Plus
v comma w.
V W.
C. So from the first principle, we derived that if the vector addition is done on the first vector, then the result will be similar to as the vector addition was done on the second vector. So it is u comma w plus v comma w, which is similar to if I would have done u comma v plus w. So with respect to vector addition, this looks rather consistent. What about with respect to scalar multiplication? Let's just
Sir, I have a question here.
yeah, please go ahead.
Sir, since you haven't defined any dual space for the current operation here,
Yes.
and the inner product space is using the properties of vector space we have defined before. So
Yes.
do we need to use the proof you currently gave us, or can we just say that it doesn't matter if u is on the u plus v is on the left or right side, we can use
That's
the
what
same
we are
property?
discussing. See, that's what we are discussing. With respect to vector addition, you can say that there is nothing wrong. Absolutely. Let's just see with respect to scalar multiplication, can you say the same thing or not? Let's just say, fine. So let's just do that. Okay. So now how to do so this is what we did. This is what? Right? Now, if I do this alpha u comma v, what will be the result of this thing?
Alpha conjugate into U
Alpha
product
conjugate
of
UV.
But how do you know that? How to derive it from the first principle? What will we do?
You can use the first property again.
Again, let's just do that
Again,
very
we'll do the
quickly.
vector
So
conjugate of it.
v alpha u star, which can be written as alpha v comma u star, and now remembering that alpha is a complex number and v comma u bracket is also a complex number, so it is nothing but the multiplication of two complex numbers, which can be easily written as alpha star v comma u star, which I can use the first again. Aha. So this is the interesting aspect. So even though there was linearity with respect to vector addition, but there does not seem to be linearity with respect to scalar multiplication. It matters to this inner product that which of the vectors, with which of the vectors I am multiplying my alpha. If I am multiplying with the second, then I have to just take it out. But if I am multiplying with the first argument, then in that case, the complex conjugate is coming out. So this is what we call as anti-linearity with respect to scalar multiplication. So now we have to be careful from this time onwards. When I am talking about u and v written in this manner, we'll have to be careful with which vector my field is getting multiplied or scalar is getting multiplied, because depending on that I will have the different results. I will have different results. Yeah. So now I will ask you to ask question in case if you want to. So these are just the properties that this space has to have, and if these properties are satisfied, I mean, I hope you understand and appreciate that the multiplication of the u with alpha on the first one, this is a consequence of the properties which are there. So I do not need to explicitly check whether this property is getting matched or not. All I need to check are these four properties, 1, 2, 3, and 4, or 3 or 4 combined to give me one direct alpha v plus beta w. That's it. These properties, if they are met, then of course it is going to meet all the other ones. So this kind of space we call the inner product space. Now, some of you may be wondering why we are coming up with this. Okay, in case of vector, we came up with it. Why we are? So if you can understand, then let's just try to explain it in some simple language for the time being. So remember, this is what our starting point, that in our quantum mechanics, we have if 2 xi1 and xi2 are the solution of the non-relativistic Schrodinger equation, then psi xt is the solution also. It's nothing but the linear superposition principle. Yeah. So all we did is something like this. We associate this guy equal to C1 is psi1 plus C2. So we are saying that this guy psi1 xt, psi2 xt, instead of talking about it as the vector wave function right now, we are calling it something like vectors in the vector space. We also know, but what? That this guy does not have any physical significance. What does have the physical significance?
Its probability given by its product, its magnitude.
Psi star psi, right? This guy, which is, okay, should not put any bar here, which is equal to mod of psi square. This is defined as probability density. Now, probability density. Probability density is a real number or a complex number?
Real number.
Real, sir. Real
Now
number.
you understand. Now you understand why I want my u comma u, which is something similar to this guy. This guy, which is a complex number, so we have to define like this, so that this is a real number. It is to make some sort of equivalence of psi star psi. We will of course make the equivalence later on when we understand this formulation completely. But the physical significance is that we have to have some properties which can take care of psi star psi to give a positive real number. This is what we are trying to achieve by defining these properties, nothing beyond that. And since all of these are the complex numbers, hence we have to be in the complex vector space. Okay, so help me out with this. What will be the inner product of u with zero vector? Or I could have written zero vector and the u vector.
Null vector.
The result will, yeah. Result will have to be a complex number, of course, and it will be zero. So you can think about it as this. Zero vector is nothing. I mean, you can think about it as 0 times any v vector which is belonging to the vector space, and 0 is a scalar. So if you do this, u comma something like 0v, which is still our vector. So let me define it like this. So 0 will come out like this. And the 0 with any complex number will going to give you 0, nothing else. So this is how any inner product with 0 vector is going to be 0. Okay, so let me now say further. These are the rules what I have defined. But what about actually defining it? So I haven't told you that if I give you 2 n tuples of number, what should be the rule which will obey these properties? So now I will give you the exact definitions, but those definitions will not be unique. Please mute it. Please mute your mics. Yeah, thank you. So up to now on, I was just defining the rule. Now let me just see. Let's say Cn C such that one of the vector is a collection of alpha 1, alpha 2, alpha n. Each of this alpha I belong to. Question number 1. Does this qualify as a vector space? for the general rule of vector addition and scalar multiplication. That means we are adding component wise addition and multiplying with scalar is multiplying every component. Will this qualify as a linear vector space?
Yes.
Yes, sir.
Yes, sir. It should.
Okay,
Yes.
so good. Homework for you is to think about the dimension. I am not discussing it right now, but yes, it does qualify to. Now, let me define this u comma v is equal to, this is I am defining alpha I beta I star. Does it qualify to be inner product space? Which means will it qualify if this is defined? So if this is defined as the scalar product, will this be considered an inner product space now? What I have done is I am saying that component wise multiplication alpha 1 beta 1 alpha 2 beta 2, so I is going from 1 to n, and instead of doing alpha 1 beta 1 I am putting alpha 1 beta 1 star. I am just defining this, whether it will qualify to be an inner product is question. How am I supposed to see that?
Properties. We'll check with the properties.
Absolutely. So please check it individually, but right now one property which I would like you to check, u lambda v, because alphas I have already taken, where lambda is a complex number. So please check this. This property should give you lambda u comma v. So whether this is matching or not. So keep your pens and papers ready in the mathematical physics class because we'll have to do it. So whether this property. So all you are going to do whenever you are multiplying a scalar with this lambda v, each one of the vector beta 1, beta 2, beta n will become what? Lambda beta 1, lambda beta 2, lambda beta n, so on and so forth. It's taking a lot. So let me just try to do it for you. So the way
No,
it
sir,
is.
it doesn't qualify.
So let me just try to do it and then we'll see. So please see, I mean, this is a single one step, but yes, it does take some time to understand it. So all I need to do is lambda beta I star, because each of this will be multiplied the second component. So your what will be your lambda v? Sorry, lambda v will be a vector, right? This will be a vector in the same vector space. What will be the components? Components will be lambda beta 1, lambda beta 2, so on and so forth, lambda beta n, right? Right? This is another vector in the same vector space.
Yes.
So the components are lambda beta 1, lambda beta 2. So the way we defined it, it is the multiplication of the first component with the corresponding first component. Now the corresponding first component has become lambda beta 1. The second one become lambda beta 2. So you can just define it like this. What will be the result of this? Now all are this is complex number, this is complex number, this is complex number. The result will be lambda star I is equal to 1 to n alpha I beta I star. These are the complex numbers with which we are working. So is this property valid now? So this becomes lambda star u comma v. Oh no, this is wrong, because now my property number 4 is not met. Any of the property fails, it cannot be qualified. So instead, if I define the same vector space, the inner product, let me define it as u comma v. So let me put this as 1. So this does not qualify. What about this 2? Yes, boliye ji.
Sir, I think it should be alpha I star, means you should take
Oh, bhai,
conjugate of.
question is not it should be alpha I star or not. Question is whether if I define certain one, whether that will always qualify or not. So first I defined it like this, and you said that it won't qualify, and now you are giving me what I have written. Yes, I agree that if you write alpha I star beta I, this is what you were trying to say, then this will ensure that all the properties 1, 2, 3, and 4 will be met. And in this case, you will find that this does qualify to be a reasonable inner product for the n-tuples of complex number. By the way, the sum of the multiplication of the complex numbers like this, will this be a complex number or not in general?
Yes, sir.
Yeah.
Yes.
It
And
may
what will be u comma u? This will be summation
Star alpha.
mod of alpha I square. Is mod of alpha I square always greater than equal to 0 and will be equal to 0 if all alphas are equal to 0?
Yes.
Yes, sir.
So please see, this is the homework which I want to give, that just do not accept any inner product to be considered as the defined inner product for the inner product space. Just like in the case of linear vector spaces, you were ensuring that once all the 10 properties are matched, then only we will qualify this space as the linear vector space. Similarly, in this case, when we are defining a particular space, we'll have to define our inner product, and we'll have to ensure that that inner product will take care of all the inner product properties. And there are 4 properties which we have written. So let me just do one more example here. So let me go to a space of this. Now this is what I defined: complex function of a real variable x. What does that mean, by the way? Complex function of a real variable. So x itself is a
Real number.
real number, right?
Real number.
Whereas the fx, it can be
Complex.
a complex number. Very good.
Complex.
And I did mention it briefly that under the simple rule of vector addition, which we do as fx plus gx, and scalar multiplication, which we do as lambda times fx, under this will qualify to be a linear vector space. Now, what will be the vectors in this vector space? They will all be complex functions of a real variable. So they are all the complex functions of a real variable. They will qualify to be a linear vector space if these 2 properties are given to you. That means that the vector addition is defined like this and scalar multiplication defined like this. Those of you who are to be explicitly clear, they can define these things here, so that this is vector addition and this is multiplication with scalar. Whereas here, now that you have a function and another function which is coming there. But anyway, the important point, let me just define f comma g inner product. So whenever I am defining, so I would like to write this, and I say in some interval, if I define this as fx g star x dx, first an integral of the complex variable, or in this case the real ones. So will this be a number or will this be some abstract quantity? Integral.
It will be a number.
Sir,
This
number.
will be a number. So at least product is defined as a number. Now question, will it qualify as the inner product space? So
No.
will this, with this definition, is this an inner product space?
The 4th property will not be satisfied.
Again, you will see if
Yes,
I
sir.
put f lambda g, then what will be the result? It will be lambda star
Lambda star
v fx, right? G star x
B
dx, which
G
is
star
lambda.
X dx.
Very good. F comma g. Hence, this is not met. So, what will be a reasonable inner product? That means
The conjugate of fx
star g.
instead of gx.
so. This is something which you may have read earlier, but I wanted to emphasize that it is not just that we are defining this to be our inner product for some particular reason. It is that I can define anything actually which qualifies all the four properties of the inner product as the inner product, nothing beyond that. Several books, I mean, if you just go back and look at Afkin will give you plenty of examples where it is defining this with some weight function, and it has given many weight functions there, and those all qualify to be inner product. So the important point to note is that the inner product is defined for a particular space in the manner such that all four properties hold true. If that doesn't happen, then we cannot qualify that to be an inner product space. So just like in the linear vector space, we have this. Now, questions here.
Sir, doubt
Sir,
is from the last
why?
page, previous page.
Doubt is from the last page, yes.
Yes. Sir, in this, the first
Exactly.
part,
Yes.
who asked us to put the lambda with the beta I?
Oh, I
Means
asked.
why?
No, okay.
Why did?
Uh, so I might have gone a little bit. So I defined u comma v as this one, fine, which is a
Yes.
complex number in general. I said that now you have to check all the four properties. When you are going to check the fourth property of the inner product space, you are going to do this.
Yes, sir.
So this is checking the fourth property. It is not somebody asked me. I have to check all the four properties in order to see if this space qualifying to be an inner product space. So what I'm supposed to do, I must check 1, 2, 3, and 4 properties which I wrote on the page of the definition. And
Okay,
what was
sir.
the fourth property? This is the fourth property, right?
Yes.
So I was just checking the properties. Yeah, I went a little faster, but I hope it is clear now.
Yes, sir. Yes.
Okay, so another homework, guys. I want to find out what will you give me as the inner product space for this. So I have set of matrices of the order n cross p defined over a complex field. So these entries are complex numbers, so components are complex, and the field is also complex. And I want to define my IPS, inner product. So give me any definition which qualifies all four properties of the inner product space. So this is a homework for you guys. Just come up with any one. It has to be a number. So your vectors will be what? Your vectors will be n cross p matrices in this case. And the rule for vector addition, vector scalar multiplication are the usual rules which you use. U plus v, that means component wise addition, and alpha u multiplying all the components with this alpha. So I want to define inner product, and I would request you to go back, look into the books, and tell me what do you find. Fine. Now,
Sir, sir,
yes.
just a question about this homework. Does it mean that we have to fix the n cross p? Like if we choose 1 cross 2, then all the members of IPS would be 1
It has
cross
to
2.
be. It has to be. It cannot be that you can make any, unlike polynomials where you have degree less than equal to n. In the case of matrices, when I am talking about n cross p, it has to be matrices. All the matrices will be of the type n cross p. So you can use 2 cross 2. I mean, if you want to. So those will have only 4 entries, but use only fixed those.
Will the multiplication with conjugate transport hold in this case? Will it be IPS?
I mean, you will have to check that. You will check it and then you will tell me. Maybe you will multiply, but then the multiplication of two matrices will be another matrix. I do not need another matrix. I need a number, either complex or real. I mean, something like a number. So multiplication itself may or may not help you. Fine, because that will be a matrix, whereas you want from this rule to come up with a number anyway. So now that I have defined length, I want to do something with the length. If I give you lambda times u, where lambda belongs to this, can you tell me what will be this? This turns out to be, let's just use the definition, lambda times u, comma, lambda times u. This is the definition of the length or the norm. So what will be the result of this guy? So there are two lambdas, each of the
lambda and u comma u.
So how are we going to do? If this guy lambda comes out of this inner product, then will I get lambda or lambda star?
Lambda star.
Lambda
Lambda
star.
star.
This guy lambda, if that comes out, then I get lambda or lambda star?
Lambda.
Lambda.
Lambda star.
So you will get lambda star lambda u comma u, right? Which will be, I could have written this as mod of lambda square norm of u, which I could have simply written. Yeah, so these are something which you can play with once you have your norm defined. But why I am interested in defining? I am interested in defining because remember, we use the normalization very regularly in our wave function. We always normalize the wave function to unity in order to have the probabilistic definition. So if a given vector, if a vector is given, so of a vector space, and I want to get a normalized vector from it, what should I do? That means, what does that mean, normalized vector? My result of u comma u should be unity 1. I want to do that. So how should I build it? How did you do it in the case of real vectors? You should be doing the same thing here. So I want to build it.
Divide by the magnitude.
We divide it by the magnitude.
Okay, so let me define my u, another vector, which I will call as u vector divide by the norm of this, or just to make sure that you guys are getting comfortable with this nomenclature or the notation, I write explicitly. So now can you show that EU comma EU is equal to 1? Can you show that? Please do it now. All you are supposed to do, 1 over square root comma u. Is it a positive real number, or is it a complex number, or it is what? 1 over square root norm. Is it a positive real number or something else?
Positive real number.
So it is a positive real number. So
Positive
when
real.
you are multiplying this, like, so you have what? U over norm u, comma u over norm u. So what will be this? Both are real numbers. So when they come out, they will remain real, because complex conjugate of a real number is a real number. So I will have what? 1 this u square u comma u, right? Which is what? Definition of norm. U comma u in the numerator, divide by mod square u. What is that? Norm square.
U comma U.
It is the inner product, which is what? Two same numbers. So just like the way you were doing with your regular wave functions, now we can think about normalizing a vector. Just like the way you normalized your vectors in the case of three-dimensional spaces, or in the case of when you were doing the wave functions, here I have given you now a simple recipe. Whenever you get a vector u, if we want to build a unit vector, or sorry, unit normalized vector, then all we are supposed to do is to divide that vector by its norm. And if it is in the inner product space, norm has to be defined. So that means we have a way of normalizing a vector. So now you are, I hope you are understanding that we are moving towards our quantum mechanics, which you read. That these rules are helping us to move towards that. Okay, let's do something more with this. a very important concept which will ultimately allow us to write down our basis vector in something, in terms of something. So is an orthogonality. What is orthogonality in case of regular vectors? You did mention the orthogonal vectors.
Inner product with other vectors is
True,
0.
true.
Inner product with, so A dot B is equal to 0 implies that A is orthogonal to B. This is our regular three-dimensional space. So we will define it here also. U and V vectors are orthogonal. Fine. It is very similar to this. So in case if the inner product of two vectors can't turn out to be 0, then they are orthogonal. Of course, I mean, if I use 0, I mean, this guy, 0 vector is orthogonal to every vector. In fact, 0 vector is orthogonal to itself also. To every vector. And this happens in the case of regular three-dimensional space also. So I will just end my today's class with a very important theorem. And this theorem tells me that if we have a set of orthogonal vectors, so let me just write down my set. Of course, non-zero. Then that set is always linearly independent. So it is a very important theorem which comes very handy, that if we have a set of orthogonal vectors, so what does that mean? That if I am talking about ui, uj, what will be the result? The inner product of ui, this will be 0. And none of these vectors can be a 0 vector. None of these vectors can be a 0 vector. In that case, that set of those vectors will be linearly independent. And how to go ahead? How to check the linearly independence?
Equation of linearity.
So
Alpha 1, U1, alpha 2.
write down
The
that
linear
equation,
combination.
right? And then if all of these alpha i's turn out to be 0, then I will say that my set is linearly independent set, right? This is the way we define it. So in order to do that, let's say take the inner product of the full equation. So inner product of the full equation with, okay, I should, yeah, I should continue with my notations. So let's say first u1. So take the inner product of the whole. So what I should be having? Alpha 1 u1 comma u1 plus alpha 2 u1 comma u2 plus alpha n u1 comma un is equal to u1 comma 0. So remember, since I am talking about orthogonal vectors, I already know that the inner product is defined for this. So I'm talking about inner product spaces only. And hence I can take my inner product set. So what will happen to this guy? What happens to u1 comma u2?
0.
0.
What happens to any of the vectors in between? They are all 0. So you are going to get the result u1 comma u1 u comma 0. This will also be 0. Right? I mean, it's a inner product with the 0 vector. So now we are either alpha 1 is 0 or u1 comma u1 inner product is 0. But this guy, by the definition, is greater than 0, as there is no vector which is a 0 vector itself. So the only implication or only inference is that alpha 1 is equal to 0. You keep on multiplying with individual u2, u3 inner product, take the inner product with that, and you will find out that the result will be that all alpha I is equal to 0, or all I going from, okay, 1, 2 to n. So this should be read as equal to. So since the equation alpha 1 u1 plus alpha 2 u1 has only one solution, which is a trivial one, that all alpha is a 0, set is linearly independent. So I will pause here in case if you have a question, please ask it right now. But I have a request, and that request is that I need another class, I mean in general, because I try to have incorporate sufficient number of examples in my classes also. And the way syllabus is defined, it is, I mean, it's strictly something like I should give only the theory, and tutorials should take care of mostly the problems. So in case if you can give me one additional class per week, not of course every day, then we will try to take certain examples of what we are doing even in our regular classes, and I can explain my concepts in relaxed manner in the way I am doing. So can you help me out with this? Give me one class.
Yes.
Yes, sir.
Yes, sir.
Yes, sir. Saturdays are off.
Yes, sir.
Yes.
Saturdays?
Sir, instead of
Saturday,
Saturdays, we can
No,
continue with
Saturday, since you
weekdays.
also have an off, please do not do that, because then you may not be able to do certain tasks which you would like to do on the whole day. So maybe
Yes, sir.
it is on the same day, maybe Monday, Tuesday, or Wednesday, in case if you have some free time, any of those days, then it will be
Yes.
Yes,
easier for
sir.
you.
Yes,
Sir,
sir.
Monday we have after 1 p.m.
Yes, sir. After
Okay.
yes, after 1:30 p.m. we don't have any class on Monday, Tuesday, and Wednesday, so we can give 1 hour in that day.
So 1:30 to 2:30 or 2 to 3, let's say, whatever suits you. I mean, what suits you? Because
Sir, it will
you
be
1:30
have
better
Two
from
to
continuous
1
4 hour
three
AM
is
to
classes.
2:30.
fine.
Since you have
Sir, two
continuous
to
4 hour
three is
classes,
fine.
you're taking the fifth class immediately afterward doesn't make any sense. I mean, I understand I will be saturated myself.
Sir,
So maybe
2:30 to 3:30 p.m.
2 to 3
okay.
will be fine.
Yes,
Yes,
sir.
yes,
Sir,
sir.
2 to
After
3 will be
2:30.
fine.
2 to 3,
Okay.
yes, sir.
2 to 3. Okay, fine. So we'll take 2 to 3. And what I will continue to do is I will continue to take examples of what I am doing along with the concepts. Fine. Uh, I hope things are clear, but please continue to ask questions in the next class is the first one when I'll be doing the summary of the questions. And maybe it is 11:05.
Sir, on
So
which day?
Sir,
Monday.
on which day? Monday.
So I
Okay,
will
okay,
write
sir.
it down on the same Teams account.
All right,
Fine.
sir. So
Okay,
Monday
sir.
2 to 3. Okay.
Monday 2
Okay,
to 3.
sir.
Yeah. Thank you. Thanks a lot.
Thank you so much, sir.
Thank you, sir.
Thank
Okay,
you,
sir.
sir.
Okay,
Thank
sir.
you,
Thank you.
sir.
Bye. Bye.
Thank
Good
you.
day, sir.
Thank you,
Thank
sir.
you, sir.